Buenas tardes, bienvenidos al seminario Fronteras de la Energía, organizado por el Instituto de Energías Renovables de la UNAM. En esta ocasión tengo el gusto de presentar al doctor Oak Nelson, que nos acompaña de la Universidad de Columbia. Y como cortesía a su presencia, vamos a presentarlo en el idioma inglés. Dr. Andrew Oak Nelson received his bachelor's degree in engineering physics from University of Colorado in Boulder in 2016, and his master's and PhD degrees in plasma physics from the Department of Astrophysical Sciences at Princeton University in 2021. After that, he was a postdoc at Columbia University from 2021 to 2022, where he currently is an associate research scientist and teaches several courses. He works on experimental and computational projects regarding fusion energy sources and engineering, focusing on the advance of the understanding of magnetic confinement fusion towards widespread commercial applications. He has experience working in several projects concerning about infrastructure for fusion energy research, applications of machine learning for acceleration of fusion discovery, fusion power plant design using negative triangularity, among others. Og Nelson, thank you very much for accepting the invitation to participate with us in the seminar, and we may start.
Awesome. Thank you so much. Yeah, it's my pleasure to be here. I'm really happy to talk to you guys today about fusion and the various flavors that it can take on. I'm happy to take questions during the presentation as well. So if anyone has a question on any particular slide, feel free to raise a hand. Otherwise, I'll just keep going, and we could also have a question session at the end. Yeah, but as said, my name is Oak Nelson. I work at Columbia University, and the topic of today's talk is fusion energy, kind of a broad overview, and then getting a bit more narrow into ongoing research projects that we're undertaking at Columbia itself. So I'd like to start off talks about fusion with a bit of a conversation about energy. I think when I was getting into fusion, I was really excited because I thought it was going to save the world from climate change. And the story is it kind of dragged on and stuff might be accelerating, but the motivation for fusion, and of course for all sorts of energy, is broader than just climate change itself. It's also just a quality of life concept that we have for the giant world. So it's no secret, of course, that the world's population is expected to grow and grow and grow, and that a lot of this population growth is expected to occur in developing nations. And then, of course, with larger population and more access to technology, including now a large need for energy in AI, we have a larger demand for energy consumption. And you can see this sort of demand for energy consumption rising over the years. Still, a large part of it is natural gas, coal, and oil. And of course, we're working continuously as the world to expand the renewables, but we really lack like a firm energy source that can help with this project. Energy use is also very strongly correlated with quality of life. You can see this in a bunch of different aspects. Here we're plotting the per capita energy consumption versus per capita GDP for different nations. You can see it's basically a straight line, but increased energy consumption is also correlated with increased happiness, with increased life expectancy, increased food, water, and resource security. And we'll note that over 1 billion people currently live without access to electricity. So finding ways not only to solve this climate problem, but also to just provide more energy across the globe is really, really important. And I think a really excellent way to motivate physics discussions. But this is all just to say that fusion is pretty multifaceted, right? It's not just climate change. We are looking to develop this energy source, and we'll talk about how we do this, to address a lot of different concepts. We need more power for AI and data economies. We need power for desalination plants, for example, or for climate redemption, or even you can use fusion plants not just for the creation of electricity, but for high-grade processing heat, which could be useful for heavy industry and manufacturing. So as we get further and further along in this technological development, we'll need more and more energy. And so there's always going to be demand for fusion, regardless of the climate problem. Right. So what is fusion? I think a lot of people here have heard of nuclear fission, right? Nuclear fission is when you split uranium or some other atom that is very large into smaller bits, and that releases energy. You can see that by looking at the energy per nuclear particle versus atomic mass here. The larger things we might use for efficient plant and established technologies release energy as we go towards smaller. Fusion is very different. Fusion starts off with hydrogen and adds two hydrogen together to get helium. Or you could, I mean, theoretically do other elements here. But you're combining nuclei to release a binding energy here, which requires some energy input, but it also has a much steeper part of the curve here. And so per reaction, you're able to release a lot more energy than you would be able to release just in fission. There are many different ways to approach fusion and lots of different reactions. There's a bunch here listed that people have considered. Here, D refers to deuterium, which is an isotope of hydrogen with 2 atomic mass. And tritium, of course, is then 3. Helium is the second element, as we know. And all of these have some sort of reaction chain, either producing a little bit of energy and a neutron, or a little bit of energy and a proton, etc. These are not all built differently. And from the perspective of achieving fusion here on Earth, we need to know which ones of these will occur most likely. So fusion only occurs by chance. We don't have the ability to take little tweezers in and grab 2 hydrogen molecules and slam them together with helium. What we need is for these deuterium and tritium to run into each other by chance with enough energy to get over the cooling barrier and get into fusion. So we can describe this sort of interaction as a cross-section, the effective area seen by colliding items. And this is something that we need to maximize. So we plotted here the cross-section for a bunch of these different reactions as the function of the center of mass energy. And what you'll note are a couple things. First, as we increase the center of mass energy, as we get hotter, we generally increase the cross-section. So hotter plasmas will have more fusion. But also that each one of these particular curves has some maximum in it, right? So for deuterium tritium, which has the largest cross-section of all the different ones we know about, it also has the lowest maximum energy, right? And so this is the coldest temperature and the biggest cross-section. This is really probably the easiest one to make. And so this is the one that most people are focusing on right now. So how hot does the plasma actually need to be to fuse, right? We know it needs to get hot. Access to fusion relevant conditions actually requires 3 different things simultaneously. We need enough plasma, enough density to ensure that the collisions happen. We need enough temperature to make sure that the particles have enough energy to collide and overcome the Coulomb barrier. And we have to hold the plasma in one place for long enough for those collisions to occur. And so the product of these 3 things, Nt and tau, is called the Lawson criteria. And for DT fusion, we need this triple product, this Lawson criteria, greater than some number, right? And so this gives us a number that we can target in order to understand if we're getting close to fusion or not, or getting close to fusion relevant conditions. You can kind of plot this here instead of just NT tau. I'm plotting N tau on the y-axis and the temperature now in millions of Kelvin on the x-axis. And again, for our favorite reaction here, DT, we can see that N tau is minimized, right? Lowest density, lowest tau at some particular temperature, which is in the millions of Kelvin, which is very, very hot. This is comparable to the center of the sun. So there are some numbers for the sun's center and the sun's corona. We're basically, in those short terms, trying to build star-like conditions here on Earth, which is, you know, a difficult task and the one that we're approaching in our research sphere. But I always think this is interesting. You know, you're building a sun on Earth, which is kind of cool. So you want to build that sun on Earth. How could you possibly do that? Well, there's a bunch of different strategies you might think of. The first, obviously, is just actually building a sun, actually building a star. Stars use gravity to keep all of these conditions going, right? They have a huge mass, and so they pull everything towards the core. Of course, if we wanted to use the same strategy, use gravity to keep our plasma confined on Earth, we would need some machine as big as the sun, and that is obviously not going to happen, so we have to rule this one out. Plasmas also follow magnetic field lines. So what we can do is use magnets as a different strategy. And this is what we'll spend the most time talking about today. Use magnets to confine the plasma and keep it in one place for a long time. Heat it up, maybe with microwaves or something like that, in order to try to generate fusion-like conditions. Another really viable strategy is to use lasers. You may have heard of the really great results coming out of the National Ignition Facility in California. These are using lasers to compress some small fuel to fusion-relevant conditions. And you can get fusion-relevant conditions here for very, very, very short-lived plasmas. This plot on the bottom, which just looks like a bunch of bars, is actually a plot of the total fusion energy coming out of these reactions as a function of year. And so you can see for a long time, we didn't have much. And then very recently, they were finally able to get break even. So lasers have had a really big break even here. They're finally able to get a ton of fusion out. But I think this is a very difficult approach for commercial fusion for reasons we can talk about later. And then there's other strategies that involve as well. People are looking at these, particularly a lot of startups. These combine aspects of lasers and magnets to find some sort of middle ground, i.e. by having some self-generated magnetic field with a strong electrical current or collisions between different bundles of plasmas, which are already magnetically confined or something like that. These are generally more complicated and we'll kind of gloss over them today. But the long story is that there's many ways to make this technology work. None of them is perfect. All of them are science fiction, and all of them have issues to solve that we can continue to work on. Regardless of the challenges, there has still been a lot of progress in the last 40 years. So remember this NT-tau parameter, that's what's being plotted on this y-axis here. This is the Lawson criteria. And up here we have some red lines that refer to Q. Q is the energy output from fusion over the energy input. So we need Q to be greater than 1 to really be generating electricity with fusion. You can see some lines here for magnetic confinement fusion, MCF, and where that kind of lies, and then also for inertial confinement fusion. Progress towards this space up here as a function of time has actually been faster than Moore's law. And this used to be true when Moore's law was running strong, and now Moore's law is kind of over. But we're still making faster progress there. So we have made a great deal of progress. And you can see these different sorts of techniques, the Tokamaks, which we'll talk about today, or lasers, or some sort of mixed regimes have all been approaching there as well. There are two big machines coming up in magnetic confinement fusion. One of them is Spark, which is being built right now in Massachusetts in the USA. And the other is ITER, which is being built in France. And both of these will, for the first time, really be demonstrations of what we think will be fusion energy greater than 1. So
Excuse me,
compared,
Oak.
yeah,
Excuse me,
please.
Oak. Where do the Chinese come in?
Great question. So the Chinese have been a big part of the ITER project for a long time. This plot is actually from a paper that was published in 2022. And right after 2022, basically China has decided that they are a bit, I'd say, annoyed with the slow progress of ITER. And so they're trying to do it all themselves. So basically, China now also has a dot up here. It's called C demo, which is a really cool one. And I think they actually have an intermediate spot called best, which will be really cool as well. And so these will also be in the similar time zone. I don't know the exact dates of when that will factor in, but China's definitely been a part of this program and should have their own demonstration plan on a similar timeline.
Thank you.
Absolutely. Yeah. And so for magnets in particular, this is also kind of interesting because we haven't had a really big machine push to limits now for 2 decades, right? We've basically been waiting for 20 years for someone to find enough money to build one of these things. And now they're finally coming online in the late 2020s. And so that should be really exciting. So yeah, this is a slightly different plot now. Now we're plotting N and tau again on the y-axis and temperature on the x-axis. And you can see getting towards this up right-hand corner, again, is the best way to go, is where progress is made. And I like this plot because it helps you separate the different sorts of approaches that we've seen. So inertial confinement fusion, this is lasers, typically live up in this space here. They have a very high density, and so this and tau parameter gets very, very large. I think these are likely more difficult to scale to commercial applications for a lot of engineering reasons. You need to have really precise alignment with your pellets and your lasers and really high laser rep rates. So a lot of the issues that are currently being faced by the laser program are really laser technology issues. And there's a lot of work being done there, but they're kind of straying away from needs in plasma physics. The second kind of bundle of points here, this is the magnetic confinement fusion approach. These are like long pulse, more moderate temperatures, more straightforward adaptation to a commercial power plant because you're just building a bigger version of the same thing rather than something completely new. And this is what we'll talk about today. And then these alternative concepts down here in the bottom, these are all those other mixed regimes or lasers or pumps or mirrors or something. These have a lot of promise for very specialty applications. For example, like you could potentially think about putting one of these on a spaceship or something like that. But I think they're likely second or third generation devices that will be quite a ways off compared to the two mainstream approaches. So I said we're going to talk about a lot of magnetic confinement fusion. I wanted to basically build up how a tokamak works, basically from a single particle orbit perspective. So plasma can be confined by the gyration of charged particles on a magnetic field. We have here a B field represented by black lines and electrons spiraling around in one way and ions spiraling around in the other. This is just due to the Lorentz force felt by a charged particle. And so basically these particles will follow the field lines. And we consider confinement basically how long do they stay along the field line before moving off of that field line. At a typical sort of reactor or fusion device environment where we have a magnetic field around 10 Teslas, temperatures on the order of 10,000 electron volts. These turn out to be the gyro orbits of electrons and ions, which means we need a device size around a meter, right? So if we are thinking back to comparing device sizes, using gravity, we need something the size of a star. Using magnetic fields, we need something the size of a classroom. These can be, quite different. This is much more approachable then. So at these temperatures that are involved, ions are moving very fast, over 1,000 kilometers a second. And the average time that we need something to fuse is still quite long, somewhere around 25 seconds, even with that maximization of the cross section. So in some way, then you have to minimize your end losses, right? You can't just have a straight field here, which lets the ions escape. And the solution here for the tokamaks is to do this by having a toroidal problem, right? We just take our field and we curl it around an axis. So now our ions are going around and around and around and around in a circle. And this ends up leading to some sort of confinement scheme. It turns out from basic particle orbits, though, we discover quite a few side effects. So this first solution we had was that a torus solves the end loss problem. But what happens then is that there's additional drifts caused by the gradient magnetic field that must be here just to make the solution. We need some stronger magnetic field in the center and less magnetic field on the outside. This leads to a drift called the B cross B grad B drift, which eventually lets charge build up on the top and bottom of the tokamak, which then creates an electric field. And once we have an electric field, then our drifts are very strong and the particles just run right out of the device. So just a toroidal field like this would basically lead to a completely infeasible scheme. And so the clever way to fix this is to add a colloidal field as well as the toroidal field that allows particles to sample both the inside and outside. So if we imagine some particle drifting here due to the B cos B drift, it will sample something on the inside, but now it's also spinning around colloidally in the device. So if it's sampling here and drifting up, that's bad. But if it's sampling here and drifting up, it's drifting towards the center. And it's kind of like a washing machine. It just averages itself out, and you end up solving this particle drift problem and getting a lot better confinement. Unfortunately, then this introduces another problem, which is that you have some hoop stress from unequal magnetic and kinetic pressures. The solution to that then is to introduce some vertical field, which just counteracts the hoop stress and pushes in the other direction. And putting all three of these sorts of fields together, we end up with the basic structure of the tokamak, which is so far the most successful magnetic confinement fusion device. This was originally created in the 1950s by Russian scientists and quickly shared, even though it was the height of the Cold War then. So I think that's the kind of a comment on the fusion field. I know stuff has gotten like very political recently with international troubles, etc. But in general, the fusion research sphere has remained really united, and lots of people are working together across the country, as they always have, even despite political issues. So this is an example of the first tokamak on one of the Russian stamps, which was quickly adopted then in the US and elsewhere as well. The whole thing kind of looks like this, right? So we have some colloidal field coils, some outer field coils. It's creating two types of magnetic field, one that spins around the plasma this way, And then we have a strong plasma current that's running around this way, which is created by this transformer circuit, which is making a colloidal field that then is keeping the whole thing together. And this actually leads to sort of nested flux surfaces as well. So if you look at a picture of the tokamak, which we'll do in just a sec, you'll see lots of different layers within the tokamak. Each one of these is a magnetic surface, and it's difficult for particles to drift out across it because each time they want to follow the layer. And so we still have a nice sort of confinement regime, which is keeping stuff in check. Right. And so typically we will use a plasma current on the order of 10 megaamps or something in a future device in order to make these magnetic fields. That's really, really large, of course, and can lead to its problems, which we'll get to later. A stellarator is a very similar type of geometry, but instead is baking in this polarial field structure into the magnetic coils as well. And you avoid having a plasma current for that reason. So what does a discharge look like? I guess I do have videos, but hopefully they're working. This is a picture of a machine, it's Alcator CMOD. And what you can see, basically, I'll pause it in the middle here, is that we have some plasma volume. We're looking right at the center stack here. The plasma itself is really invisible, and that's actually because it's so hot that it's not producing any visible light through electron emissions. When it gets closer and closer to the walls, it cools down a little bit, and then there are just valence electron jumps that produce visible light that we can see. A reconstruction of this might look something like this. And so this is a plasma evolving in time where we're plotting different magnetic fields over the 2D cross section. So this sort of plane here is actually corresponding to this part of the plasma right here. And you can see those onion-like structures that I was talking about. These are magnetic field lines that keep everything confined in one place and prevent the plasma from moving across. From a user perspective, tokamaks are really big. They're very large machines. They typically require a whole facility to run, so they're typically not found there are large tokamaks, at least, are not found at universities, but rather user facilities around the world. These are pictures from the tokamak in San Diego, California, where you have some control room with different plots and traces of the plasma density or the different beams that are going in. This is kind of what that control room looks like in action. You can see it cross section. This is a picture of the tokamak itself, tons of different diagnostics going into it, tons of different ports. You can barely actually see the vessel. The vessel is kind of hidden here, and everything else is something that's supporting the tokamak, the heating scheme or something like that. This is a picture of the inside. So it really does feel like you're kind of in like a space control room or something when you're operating these things. So really fun. So we talked a bunch about the tokamak. I just want to briefly mention that there's a bunch of other ways to create magnetic confinement. Basically, all of these are just different solutions to grad cross B equals mu J, right? The pressure gradient balance. There's several different ways you can do it, starting from a very simple geometry, where you have some sort of like cylindrical or linear geometry, or cylindrical geometry with different magnetic fields to pinch the plasma together and keep them from going out, to toroidal geometries with different types of current along them. This one here is the tokamak, where we have a large toroidal field and a large plasma current to create a colloidal field. And of course, I also mentioned the stellarator, which has a more complicated geometry where you're actually baking the magnetic field into the magnets itself. These are typically simple. They have high beta. Beta is the ratio of pressure, plasma pressure to magnetic pressure. So they perform quite well. However, they have low chi. So this means that they're going to transport very, very highly, and basically you can't keep the plasma there for a long time. As you get more and more complex, you can keep the plasma there for longer. You avoid your drifts, but you also lower your maximum beta. And so there's kind of a trade-off in these different approaches. And so far, the one that's been the most promising is very much towards this side of the spectrum. Great. So that's a quick intro to different tokamaks. I wanted to move now into active tokamak research areas, particularly ones that we're looking at Columbia. There's a bunch of different challenges that are faced by the fusion program. they are highly interdisciplinary challenges. So I'm a plasma physicist, but the remaining challenges towards building a commercial fusion energy system are really varied, and they can be anywhere from the plasma physics, which is kind of here, advanced confinement approaches, um, to just electrical engineering. Fusion plant engineering systems integration still has a lot of challenges for a device of this size. We have the intersection of plasma with materials, right? You're holding something as hot as a star with a metal, and we don't have any sorts of metals that can withstand the heat flux from a star. So there's a bunch of materials science that goes on here. There is a bunch of open questions related to the fuel cycle and tritium processing. How do you extract fuel from or exhaust from your device and then put it back into your device to keep the plasma going, to keep the reaction sustained? Um, of course, we also have a blanket here, which is extracting heat from the device. And we've never made a device hot enough to really test this. So there's a lot of questions open with blanket science and technology. How do you actually convert this heat then into electricity to go to your grid, etc. There's a little robot arm sticking up here. These will be very, very, very difficult environments. And so we think that something like remote maintenance is really essential. And so there's a big program in the UK that has been looking at remote maintenance and trying to find out how to design robots to go in and fix different parts of this, since a human can't access this, etc. So it's a very interdisciplinary field. Lots of different people coming from lots of different places to work on this together. And plasma physics is really at the center of what we're doing at Columbia. So there's a bunch of different ideas up here on the screen. I'm not going to read them all, but these are all different sorts of needs that we have for the giant plasma project that we're working on for fusion energy. And a lot of these are related to making basically the core edge problem a solution. And so I'll describe that in a bit more depth in the following slides. So these topics all revolve around a pretty simple central mission. Basically, here again is our cross-section of a tokamak. In the core, we need to establish a core plasma that is stable and at fusion-relevant conditions, right? So we need to have a star. And it must not destroy the machine, which is kind of difficult to do, right? If you think about temperature gradients that exist in nature, here we have something on the order of several millions of Kelvin, and here we have something that's room temperature, right? So that's a very, very enormous temperature gradient. And it leads to a lot of instabilities and a lot of different things that are emergent phenomena in plasma physics, which are very interesting to study. So the core plasma typically is a turbulence and MHD problem. So this is a picture of a turbulent simulation run by some researchers at the Princeton Plasma Physics Laboratory, where we're actually solving first principles turbulence and magnetohydrodynamics within the tokamak itself to understand how energy and how particles are transported from the hot and dense core region outward across the device. Eventually, this sort of transport will lead you out of this confined region towards field lines on the outside. They're marked with dashed lines here. And each one of these dashed field lines actually intersects the wall. So this is called the scrape-off layer. And there's a big transport of energy and particles from the core, which is hot, out of the plasma into the scrape-off layer, where then it will go and interact with the wall. And again, these are very hot temperatures that eventually need to cool down before that happens. So these sorts of confinement regimes can really depend on a bunch of different things. And there's lots going on to set how the core performance looks. One of the very, very common ones, and you'll see this a lot if you look into the fusion tokamak research, is called low mode and high mode, or L mode and H mode. These look something like this. So here in this plot, we're plotting 0 to 1 is a minor radius of the plasma. So 0 is exactly in the core, and 1 is at the outside. And basically, there's two types of operation modes in tokamaks that we've discovered empirically. The first is L mode, which has a profile that looks like this, where the y-axis is plasma pressure. So it's low at the outside and then higher on the inside. It turns out that if you heat your plasma up enough, the plasma will do something miraculous for you and self-induce a transport barrier where you get this very, very steep region of gradients in the very edge, which basically lifts your entire core profile up to a higher plasma pressure without changing too much the gradients in the core region. And so this is a really big boon for fusion because it allows you to get to much higher temperatures, much higher densities in the core. But to sort of illustrate the challenges that we face, while this extrapolates very well to future energy confinement schemes due to the enhanced pressure from the pedestal, it also comes with a downside, which is ELMs. ELMs are edge localized mode, and these deliver really large transient heat fluxes to the plasma-facing components. So what is an ELM? An ELM is basically a periodic collapse of this barrier where it shifts up and down. And you can see a picture of one here. You can see some toroidal and colloidal field lines here, where there's actually hot plasma connecting to that cold plasma on the outside and delivering a big burst of energy. As a function of time on the x-axis here, you can see these spikes pop up in the diverter light. And so in an H-mode experiment, typically you'll have giant spikes of ELMs, which are very, very sharp deliveries of energy into your wall, which can actually eventually melt your plasma-facing components, melt the metal around your outside of the device. This is really bad and can't be tolerated in a fusion power plant. So there's lots of modes or research going on to understand how you might access H mode without ELMs, or potentially get to a different regime that has some improvement over L mode, but doesn't lead to these periodic instabilities, etc. And that's a big part of what we're doing at Columbia as well. Now, there's also a lot of work that happens outside of the core plasma in the diverter region. So the diverter is basically this space down here where the plasma and energy flows are interacting with the wall. This is the quote-unquote trash can of the tokamak, if you will. It's responsible for moving most of the heat and most of the fusion products, and it has to be able to tolerate all these sustained heat fluxes and particle fluxes, which are similar to a spacecraft coming in re-entry. And there's no real material in the world that can do that without some help from the plasma. So from a plasma physics perspective, we have different ways to try to mitigate this impact of heat flux going into the diverter. So for example, one of the ways we might do this is to add impurities into the plasma. These are higher Z elements like xenon or neon or something to increase radiation in the scrape-off layer. And so what you can see in this sort of plot is an experiment on D3D where we did just that. We were puffing in a little bit of extra neon in order to radiate away energy before it released to the wall. And what was able to happen, well, the density stayed quite the same across all of this different region. The temperature is hot in the core plasma, but is dropping precipitously as it gets towards the edge, right? So this is really interesting because now we can have a hot plasma, which is basically separated by a layer of radiating gas from our machine. And by the time it gets to the machine walls, it's cold enough that materials can withstand it. This is a great solution. However, it also makes the plasma unstable. So this might come with events called MARFs, where this sort of radiation front would push back up into the core plasma and then start to cool down the core plasma. And then this leads to loss of confinement, which is really, really bad. And so we have to be able to precisely control where this radiation is happening in this extreme environment. There are also sorts of engineering problems or solutions that could be imagined here. So for example, different shaping and super X configurations are kind of shown here. This is from a tokamak in the UK, where we're changing the shape of the magnetic field lines in this region from something very, very simple to something much more complicated. And these complicated shapes, while more difficult to achieve, can help to spread out this heat flux over a larger area. This also, you can imagine, gives us a different volume in which to do radiation and potentially keep the radiated plasma away from the core. All of this brings together material interactions with core plasma physics, with neutrals, with radiation. It's a very complex, difficult to control environment, and something that's an active area of research. So we mentioned ELMs. ELMs are something that carry a lot of energy towards the wall. And I didn't show this graphic, but I love to show this graphic because it's just kind of fun. I like to imagine this low confinement in H mode, basically as a faucet turning on more water. In low confinement mode, your faucet's running kind of smoothly. In a high confinement H mode, you turn up the faucet and the plasma builds a bucket for you to keep itself in. And so you get something for free. But unfortunately, that bucket eventually overflows and you get these big heat fluxes on the wall. These are periodic. And they're not actually even the worst issue that we face for tokamak plasmas. There's this thing called a disruption, which is even worse. This releases all of the plasma energy all at once. And so this entire bucket would just disappear, and the whole filled up bucket would dissipate onto the walls at once, which could be very devastating. So disruptions are a rapid and complete loss of current and energy from the tokamak. And this is actually a really big threat for a tokamak, and one of the big reasons people are still interested in stellarators, even though they have slightly worse performance, because stellarators don't have plasma current, and so disruptions are not as much of a problem. Typically, a disruption can be tolerated on a device of today's scale. And so this is a picture of a disruption that happened at the D3D tokamak in California, where as a function of time here, we start up our plasma pulse, we get to some plasma current just over a mega amp. In typical normal operation, what we'd love to see is that we're able to sustain this for a while and then slowly ramp it back towards zero. However, in this shot 157444, something happens around 4 seconds, just before 4 seconds, that causes the plasma to release all of its plasma current at once into the walls. And this can happen for various reasons. Either you can have something inside the plasma create an instability, like an island or a tearing node that leads to loss of confinement. You could have something fall in from your walls. Imagine if you have tungsten walls and a little piece of tungsten falls in, suddenly you have a very highly radiative thing right in your core. This could lead to a radiative collapse, which also leads to disruption. These can be tolerated in present-day machines to some extent. There are reports of larger machines having like big physical jumps when something like this happens. And if you calculate the sort of force that we expect to see in a full-blown unmitigated disruption for either spark or ITER, this gets up to very, very large numbers, 20 kilograms of TNT or 100 kilograms of TNT. This is a big event. And so the device will not be able to tolerate many of these. There's a bunch of active research in order to avoid disruptions. This is prediction of when they'll occur, active control to steer the plasma away from conditions where it's dangerous. This is a big place where machine learning is coming in. And there's also techniques we can have to mitigate the effects of this, either by shooting in lots of pellets or gas, basically to try to cool the plasma. Once we know this is coming, we can cool the plasma a little bit in order to mitigate the effect of the disruption. And so this is a big question mark for future commercial implementation. And then very briefly here, I also wanted to say, before talking about some of the stuff we're doing at Columbia, that diagnostics are also a very key part of tokamak research. This is a picture of the inside of the D3D vacuum vessel, and you can see lots of different elements here of things that we're measuring. And so, of course, this is a big multi-institution user facility. There's lots of stuff going on here. And you can see each of these different facilities that is contributing something. GA, UCLA, LNL, ORNL are responsible for different devices. This is a really, really, really great system on D3D. But the challenge gets very much greater in an FPP, a fusion power plant, because neutron and energy fluxes are going to damage all this equipment. And so we have to figure out how to design diagnostics that can tell us what we need to know about the plasma operations while still surviving the very, very harsh environments inside a tokamak. And so this is a very active area of research as well. Cool. So continuing on, I'll talk a little bit about the Fusion Research Center at Columbia and stuff that we're doing today, and what our academic responses looked like to changes in the field. So most notably, I think you may have seen in the news, right? Fusion looks very different today, or at least the fusion landscape looks very different today than it did even a few years ago. For example, funding by private venture capital into private fusion companies, at least in the US, has now exceeded all of the traditional government sources. So we're doing a transition from government-sponsored research to private-sponsored research, which is happened very, very rapidly within like 5 years. And there's also now a very large stakeholder, both government and private, interest in commercialization. So this is moving from a basic research area into something that the world wants to commercialize and make money off of. And so this has inspired a lot of continuing support, despite higher interest rates, inflation, macroeconomic, macro-political issues. But it also requires that we have some level of technical success to have future funding. So while a government program is slower and well supported, it can also last a lot longer. And the private support that we're getting from Fusion now is much quicker, but it's contingent on actually getting one of these things to work and being able to build it. And so that's a very different research environment. It has come along with a tremendous surge of interest from young people. So one of the things that we've been thinking about at Columbia is really what should our academic programs, how should our schools adapt to this changing environment, and what should we do in response to the changing times? So at Columbia, our basic strategy has been to try to grow as much as possible while we can and help to catch up. So fusion is really studied only in a couple places in the US and then a couple places globally. And so competition for talent and resources at the university is quite strong. And it's within a school, it's typically kind of between fields. There's been a very large surge of interest in fusion, which has propelled participation in our group, including a lot of undergrads. And so you can see over the course of the past 5 years, or 4 years even, we've gone from around 10 members in our lab to almost 120. A big majority of these are undergrads, but a lot of them are grad students as well. We now have about 30 graduate students, a couple postdocs, around 5 scientists, and a few professors as well. So lots of different interests, and it's growing quite strongly, which is really fun to see. And this has really supported 3 different
Excuse me,
Yeah, please.
what do these depressions mean in 2024 and 2025? Why do they go down?
Yeah. So that's a great question, and exposes some of the methodology that I'm using here. What I'm counting here is the number of weekly users on our Slack channel, right? Not actual people enrolled, but people that are actively engaged in our Slack discussions. Each one of these is the winter holidays. So people don't like to work during the holidays, which is great. Love that. Yeah, great question. All right, so yeah, so our program at Columbia is kind of divided into 3 pillars. We have a couple on-campus machines. We have 2 Tokamaks, HBT, EP, and a new one called Qt, which we just got from the University of Washington. And we have a small Stellarator, CSX. These are very much smaller than the ones that we saw at D3D, and are operatable by students to do various experiments that are very related to their thesis example. So this gives us a pretty good engagement with an on-campus program. There's also a lot of different facilities that I haven't pictured here, which are describing fusion technology and diagnostics and things like that. So this is one of our big 3 efforts. About a third of our people work here. And then a third of our people are also working on data analysis and experiments and modeling support, actually, for large tokamaks and now stellarators as well. So I mentioned D3D and ITER quite a bit. These are 2 big machines, now much bigger, 6-meter, and ITER is going to be absolutely ginormous, 28 meters across. We work a lot with these programs. This is the mostly government-supported work that we do, still getting our funding directly from the Department of Energy at the US or international partners to work on these large user facilities and really conduct state-of-the-art plasma fusion research that can't be conducted at an on-campus facility run by students. And then new to what we're doing at Columbia is actually starting to engage a lot more with these private fusion startups. So this is a list of the startups that we've been working with. Each one of these has its own specific contract with our fusion center to investigate various things. And typically, well, some are longer. Most of these contracts last somewhere between 6 months to a year. So these projects are much shorter and need delivery on a much faster timescale. And it's turned out that most of the work done for these projects then has been completed by scientists and postdocs in the group who are able to kind of tackle an individual problem quite quickly. Whereas most of the work for the fundamental plasma physics on large tokamaks turns out to be the work of graduate students for their thesis, et cetera. So we kind of have some artificial division between where the scientists are working and where the graduate students are working within Columbia. And then new in 2025, we have an REU program through the NSF. So if you have any students that would like to come work, we have opportunities for them to work on stuff during the summer. So a couple different major themes that we've been working at Columbia. I'll spend the most time talking about this one. This is fusion systems design. And so one of the things we've been really trying to champion is the development of open source codes that we can use to address issues in tokamaks and also stellarators, and using those to conduct real research in addition to establishing them as pedagogical tools for the development of a fusion workforce. And so this kind of follows a long history of fusion design in fusion education. This is a slide that we borrowed from Professor Dennis White at MIT, where it's showing a bunch of different constructions of different devices, starting off with something like this. Then the arc sort of things, they looked at a space planet, interplanetary fission fusion reactor, and a high temperature L mode reactor, and a negative triangularity reactor. This particular design, which was completed through a course led by students, led to the spin-off of Commonwealth Fusion Systems, which is a company now building Spark. At Columbia, we've really carried this tradition along, and I've worked on 2 different designs in the past couple of years. These are mainly student-led projects, which are really cool because it establishes a way for students to get involved with all elements of fusion research. So there's 2 different machines that we worked on here. One was called Manta, which is available in the publications at this QR code. This is a negative triangularity reactor that's a fusion pilot plant. And then we have a smaller version. You can see a person for scale on these 2 images, which is what we've been working on now, publications coming out soon, which is supposed to be a next step-like device to demonstrate negative triangularity as a different path forward. So looking at new options. What we're talking about here with negative triangularity is an interesting sort of exhaust solution that has recently come into the public light through a bunch of experiments in Europe, in Asia, and at D3D. This basically flips the shape of a tokamak and provides some sort of solution for exhaust. So with strong magnetic fields, we can actually flip the shape of the cross-section. If you remember earlier, we had a larger part of the field going towards the core and a smaller part of the outside. In Manta and Centaur, what we've looked at is flipping that so that the shape, it actually makes some sort of bow tie configuration instead of like an apple. And this was originally thought about in the 80s and kind of dismissed as a bad idea because it led to worse confinement. But since then, we've had a lot of improvements in confinement, and now it actually seems like it's a good idea to do something like this, because while we have a little bit less confinement in the core, we also get rid of H mode and ELMs. So we don't have any of these edge localized modes, which we know can melt the walls. So we're basically sacrificing a little bit of core performance in order to have a better exhaust solution. So thus the yin-yang type of thing. A little bit worse core, a little bit better exhaust. Can you turn this into a viable reactor design? And so the students worked a lot on this to come up with these 2 designs, basically taking targets from large international, or in this case, Mason is just from the US, but there are also international reports of what should a power plant sort of look like, and turning those into different designs, meshing every part of the reactor together to optimize these things for negative triangularity and to perform an economic analysis to make sure that they're viable. So this systems design class was really based around interfaces. How does it work in practice? Well, in practice, we had 5 different groups. One group looking at core plasma physics, one group looking at the scrape-off layer where those open field lines are and you have a lot of neutrals, one group looking at economics, one group looking at magnets, magnet performance, superconducting magnet technology, and another group looking at the blanket. So how do you get energy in and out of the device? And each one of these different groups interfaces with the other groups in different ways. And so the way this course worked then was that we would have each group go and solve its issue and then come back and during the course time have a discussion with the other teams of what was good and what was bad. And inevitably, economics group wanted everything to be really small, but then the neutron group needed some shielding and the core group needed to be big to get plasma performance. And so you got into a bunch of science arguments and needed to find compromises that would lead to a self-consistent picture of what this reactor looks like. So I think this was a really, really cool environment. I would have loved to take a class like this as a student because it kind of opens you up to this interdisciplinary approach to plasma physics and fusion. And it's been really successful, each one of these coming out with a publication that describes the full device. In the process of doing these courses, we have also been developing a set of open toolkits, which then can do a lot of the different analysis that we need for different types of fusion design and hosting them online. So this is an example called Open Fusion Toolkit, which was primarily developed by my colleague Chris Hansen. It's all fully open source on GitHub and allows you to do various different things within the tokamak environment, including create reconstructions of your plasma and look at the magnetic field stresses and the coils, looking at time-dependent modeling of MHD, magnetohydrodynamics, or electromagnetic effects in your walls and in your plasma and how that impacts your fusion design. Right now, we're actually in the process of coupling this also to an internal transport code. So you could look at transport physics and stability physics as a function of these different design spaces. And all this is available for free online. You can look at an example if you want to go build your own tokamak on our website here. And it's a really great place to interface. And in addition to building these up as pedagogical tools, one of the really cool things about having everything open source is then we can also engage with these tools in the private sector. So typically in our work with the private sector, what we've noticed is that a lot of the things that people want us to do revolve around some design that they're keeping secret, right? However, the plasma physics for that design is still quite open. And so there's this weird dichotomy in fusion private fusion research where parts of the research are need to know basis and behind IP. And the plasma physics for that research, which benefits the whole field, is typically published and open. This has been an interesting landscape to navigate. So for all of these different companies, we've interacted in a bunch of different ways, but having an open source physics framework with which we can interact with these companies allows us to keep the physics open as a research environment while looking at particular examples of that physics that might be closed under private IP laws. And so this has been a work in progress. We've really just been doing this for the past few years, trying to adapt to the new surge of funding in the private sphere. But so far, it seems to be working out quite well. So yeah, these private fusions come up with a bunch of different pros, right? They're leading the charge for new facilities, and we have a feeling of more tangible contributions with near impact. The cons are usually that they're not doing brand new stuff. They want to do proven stuff. And contracts are usually very short. And so we've tried to have the same person work on both industry and foundational work so that we can push forward on something in our government contracts while doing the same thing again for industry. But it cannot really fully substitute curiosity-driven elements. I think there still needs to be some sort of public sphere for the research here going forward. Just a couple of examples of what private companies are working with and different things, right? So I talked about system design type work. That's mainly here, but we also have plasma physics projects, like actually dedicated plasma physics projects that we're working on with other companies. An example of this would be developing 3D informed 2D pulse design models where we can start off with some ramp up simulation, look at how different fluxes and different eddies are developed in the conducting elements of the vessel wall as a function of time. And then eventually resistivities in these regions can be projected onto like a 3D thing in order to actually engage with experiments and understand how 3D models can be used in plasma physics. I think I was running towards the end, so I'll skip a few slides here with more of these examples. We can come back to them in a bit. Just to talk about two things that I'd really like to mention. One is the Columbia Research Center has actually just come up with a fusion energy miner, which is something I'm really excited about. And so this is something that I think can be modeled across the globe, basically finding new ways to get undergraduate students engaged with fusion energy or other renewable energy sources and other renewable energy threads early on in their career. So this is new this year at Columbia, and it's been a fun way to engage with more students. And then finally, I wanted to make an announcement about Fusion Energy Week, which is a big international week that we have celebrating fusion energy. There are some examples from last year up here. But basically, this is a grassroots organization that allows different people around the world to host an event in celebration of fusion energy during a particular week, so that we can all kind of share our own enthusiasm and really spread the word to develop the pipeline. So we have a nice website for this, which you can see. The week is coming up in May, and already we have a bunch of events around the US, and I've one in Europe, and a couple more that I know of that are coming in New Zealand, although they're not quite up yet. So if you guys wanted to host an event down in Mexico, I'd be very, very happy to work with you and figure out what that might could be. If you look at the types of events we've hosted in the past, they're all over the place. We have, tours of actual fusion facilities to remote presentations to schools literally hosting like an art drawing contest. So it can be very serious, it can be very silly. All of these things are great. Another type of event basically is a fusion energy trading card collection. So these are available now as material for different events to host. So I think that kind of brings me to the conclusion of the hour. I'm happy to have any questions, and I think I'll just leave this slide up as sort of a reminder. So yeah, please, thank you for your attention, and I'm happy to talk more.
Thank you all for your really interesting presentation. So we open the question session. Please raise your hand, and you can ask directly the speaker. Professor Mariano Lopez Dero, please.
Thank you, Filiberto, and thank you for a very nice presentation. And I have a couple of questions concerning, first, when you have this page, I haven't seen it, build your own tokamak. I'm curious about the kind of cost that would involve.
Yeah. So there are lots of different, yeah. There's lots of different levels of fidelity that you could build a tokamak with, right? Of course, if you're trying to do like a full first principles gyrokinetic turbulence model of the entire device, that requires 7 months on a giant supercomputer, well beyond the scope of anything, right? At Columbia, what we're trying to do is expand the pipeline for fusion research quite a bit. And the motivation for this being, if you believe the private timelines that are saying they're going to have fusion energy on the grid in the 2030s, what this also means is to have like an actual impact on the energy sector, we need to have hundreds of machines on the grid by the 2050s, right? And so we need really an exponential growth in the pipeline of engineers and scientists that are engaged with fusion. And so this build your own tokamak site, which you can go check out yourself, is actually quite simple. It can be run on your laptop. Basically, our students put this together to run a student course, but I find it quite approachable. You can open up a Google Colab notebook, and this takes you directly to a page where you'll load up Tokamaker, which is one of these open source tools that we were talking about from the Open Fusion Toolkit. And you can set up your device geometry. It gives you some examples of what that would look like. You might want to place your coils in various places. You create a mesh. You can talk about your plasma profiles, and then you eventually solve a solution. And then there's a bunch of different exercises you can do after the sort of solution to maybe optimize it to see what sort of performance you might get, etc. So it actually runs just through this Google Colab notebook online with the power of your laptop, and is meant really as sort of like an introduction to get people engaged with tokamaks, not as necessarily a research tool. However, I'll note that the same software does power actual physics research, right? So if you want to bridge from here to real research questions, we can engage with you and talk on that matter. And that's certainly viable as well.
No, I was just curious whether you could actually build one, or whether it was
physically,
just as you say. Just that's right.
Yeah.
That was what I was wondering. I think you could eventually do it, but I was wondering about the cost.
Yeah, great question. So yes, you could actually do it, and we're working with 2 private companies right now using this software
Mhm.
to help design the actual machines that they want to build. Um, these machines, depending on the size, are very expensive.
I guess so, yeah.
The large ones like ITER, and part of the reason we've been waiting for 20 years to build it is the price tag is something like $30 billion US. Very, very expensive. Um, this is one of the big issues for commercialization is we need to find ways to make that cheaper, right? And of course, the first of the kind plant is going to be much more expensive than anything else.
Mhm.
Eventually, we can manufacture stuff in bulk, but um, that is one of the different sorts of challenges that we face. Another project that we're working on is fuseexplorer.com, which you can go check out as well. This has it uses a different code made by General Atomics called Fuse
Mhm.
to show a lot of different types of designs. I'm hoping this will load in time. Yeah, a lot of different types of designs, varying different parameters. And you can actually like look at how different uh, changes in your design might change your capital cost for these machines.
Mhm.
So you can see here we're able to find a machine that looks something like this, which gets down to around 15 billion for the first of the kind. Still very expensive, right? And so there's lots of challenges here that need to still be addressed. Yeah, this is by no means easy or solved.
Thank you. The
Yeah,
other question I have, if I may, Filiberto, may
yeah.
I? Yeah.
Yeah, yeah, go ahead.
Okay. Is how about I was not surprised, but it really impressed by the amount of uh, uh, capital investment in these companies that are really betting for the future of fusion
Mhm.
energy. And I wonder how what do they expect for their capital return? What's the time period that they are expecting to get their capital return back? Because that's a huge amount of money, at least
Yeah.
in my pocket. Okay.
No, it's a giant amount of money. Yeah, I have some mixed feelings about this, to be honest. Um, I guess there's a fact that needs to be said, right? That this is distributed over hundreds of companies, so it's not
Uh-huh.
all at one place, right? Which reduces it a little
Right.
bit, but um, it's good and it's bad. It's good in the sense that it lets us try more things, right? So we don't have all our eggs in one basket. But it's bad in that a lot of the companies that are starting up right now um, are, I think, at some level, just cash grabs from investors and aren't really like ever going to be able to deliver on the timescales that they promise. Um, and that's something that we certainly look at when we're trying to engage with the company through Columbia, is whether or not we think their physics is viable. But I mentioned a lot of these sort of alternative concepts as well. Many of the companies are chasing alternative concepts and promising timelines in the
Wow.
next 5, 10 years that are consistent with like the mainstream approach, an optimistic mainstream approach, right? And I'm very, very, very far from convinced that they'll be able to meet those. Um, which makes this sort of time in fusion pretty interesting because I think there's going to be a big surge of interest right now. And then there's going to be a lot of failures, maybe some successes, hopefully some successes, but a lot of failures in the
Awesome.
next decade or so. And that's also going to color the funding landscape again, especially if the public sphere for fusion gets so attached to these private companies and then sees that they all fail and starts to think that fusion's impossible and then gets really discouraged. That could be bad for the field. So there's definitely a lot of uncertainty in the future. And that's one of the reasons at Columbia we're trying to have like a multi-pillared approach, right, to engage on different fronts to hopefully ensure stability for the program going forward. Um,
Okay.
the most promising companies are promising quite a long time scale still on cash back. So, for example, CFS has been around for the better part of a decade now. They are turning on their demonstration machine this year or early next year. And that will basically just be a machine that hopefully proves their approach
The
is
concept.
viable. And then they have
Concept.
to build
Yeah.
another machine which proves you can connect it to the electric grid, which would be
Mhm.
in the mid 3030s or 2030s. And then eventually they like their timeline says that they want to start putting these everywhere in the 2050s, right? So that's from 2020 to 2050, like a 30-year long time scale before you really have capital in turn.
Right.
Um, which is yeah, a lot to stomach.
Okay, well, let's hope that the time scale shortens, but I don't think it will.
Yeah,
Anyway,
I think I agree with you.
thank you. Thank you.
Thank you for the questions.
Thank you. We have time for one more intervention. Professor Sergio Cuevas, go ahead.
Thank you very much, Philly, and thank you Oak, for a nice and complete presentation. It was really very interesting. I would like to ask you something about comparison between the ITER project and all the other small projects, or well, I don't know, probably are not that small, but anyway, not of the same scale as the ITER.
Yeah.
So in terms of probability, what do you think about the possibility of getting the goal of commercialized fusion? So it appears, well, I'm not very close to the field, but anyway, it appeared when the ITER was launched that it was going to be the project in that would have the most possibilities to get this goal. But now I'm not sure that is what is going to happen. Could you comment on this?
Definitely, yeah. So ITER has been a long time coming. I think back in the 90s is when people started to really invest in this. They're going from the machines that we have now towards a commercially viable machine. There's basically two approaches. One approach is to make the machine much bigger, to get a larger radius to confine the plasma for longer. And the other approach is to get much stronger magnetic fields to squeeze the plasma harder to keep it confined. And when ITER was designed, the magnetic technology to make stronger magnetic fields was not available. And so that wasn't really an option. And the only way to make ITER was to go very large. Spark is taking the magnetic field strength approach because they're building off of magnets that weren't available when ITER was designed. So we are exploring both approaches now. ITER has had a lot of challenges in its construction, mainly because of international political things, i.e. there's a lot of difficulty in organizing a big international project at this scale with components coming from Korea and India and the US and the UK and like all over the world and using different units and different timelines and different cultures. And so that's been a big source of the delay in ITER. The physics for ITER and the physics for Spark are both very well established. And so we are pretty confident that both of these will be able to produce a Q greater than 1 plasma. In terms of commercialization, then the question really, I think, comes down to the cost. If you have a bigger machine, it's likely going to be more expensive. And so towards commercialization, from my perspective, at this moment in time, and maybe I'll give you a different answer if we come back in 5 years, but right now it seems like the approach that Spark is taking to make very compact machines with stronger magnets is more commercially viable than the big approach that ITER is taking. But of course, that still depends on both of them actually reaching the plasma conditions that we need. So yeah, there's kind of these two different approaches now, strong magnets and large size. And both have yet to demonstrate Q greater than 1, but the physics for both seems very consistent with what we know. So really, it will become an issue of are there additional physics questions that we haven't learned about yet that might be showstoppers? And if not, what does the economics of these things look like? Is it better to build a bigger machine, or is it better to invest money in stronger magnets, which are more expensive, right? And so those questions have yet to be answered.
Okay. Thank you very much, Joe.
Yeah.
Okay, so due to time issues, we have to end the seminar here, but if Oak has time after the seminar, we can ask the last question, okay? So thank you very much, Oak, for your nice presentation, and thank you all for your attention.
Yeah, thank you so much.